All right, so we covered all of these things here, and I want to talk about, I'm going to move on, and we're going to copy this same table here, and I want to talk about this concept of independent events. Okay. Independent events are events where the outcome of one, or I'll say if two events are independent, then the outcome of one has no influence on the outcome of the other event. Okay, so what that essentially means is that the probability, so I'll write, so if events A and B are independent, and what that means is that the probability of event A given event B is just the probability of event A, meaning whether we know B has happened or not, the probability of event A happening is just the probability of event A. Okay? So likewise, probability of A given if we know B has not happened. So if we know not B, what is this going to be? Same answer, probability of A. So whether event B has or has not happened, the probability of A happening is just the probability of A. All right. Does that make sense? Yes? Okay, so then let's look at our chart over here. I want to ask, is being male independent of, we'll say, being conservative? Okay, this is a question we want to ask. All right, so if they are independent, then what will be true? If these two events are independent, then what will be true? Okay, these equations up here will be true. Okay, so let's just call A being male and B will be being conservative. Okay, so if I just replace, let's look at this top equation here. All right, and I'm just going to replace where I see A with male and B with conservative. Okay, so what is that going to give me? If I look at this, what am I going to get? I'm going to just replace. So what do I have? Probability of. No, just tell me the words that I'm writing. What?
Male given conservative.
Okay, male given conservative. Thank you very much. And this should be equal to what?
Probability of male.
Probability of male. Okay, are these two equal? No? Okay, so what is the probability of being male?
0.46.
0.46, right? 46 out of 100 or 0.46. What is the probability of being male if we know someone is conservative? 20 out of what? 20 out of 29. Okay, and so what do I get there? 20 divided by 29 is 0.6897. Okay, so 0.6897 is not equal to 0.46. Is not equal to 0.46. So we conclude that they are not independent. That being male and being conservative are not independent. Now I want to make sure conceptually this is okay. No? I got shaking heads over here. We'll try another example. So well, I just want to make sure, is the definition of independent events okay? Susan? Just that if events A and B are independent, then the probability of A given B should be equal to the probability of A. Is that relationship okay? Yeah? Okay. So you're nodding over there, so that's good. And so when I ask this question, is being male independent of being conservative? To answer this, I'm going to see if this relationship holds. If this relationship holds, then that means they are independent. If this relationship does not hold true, then these two things are not independent. So to put these into the equation, I have just labeled, I said whenever I see A, I'm going to call that male, and when I see B, I'm going to call that conservative. So I've just filled in A and B. I replaced that with male and conservative. So I got probability of male given conservative, is that equal to the probability of being male? Okay, so is the transition from this relationship okay to here? I'm just checking with Susan here, just making sure that part's okay. All right, and so maybe this part went quickly, but we then calculate these quantities here. Okay, and so I think on the previous pages in your notes, it should be clear how we calculate this. Male given conservative, we look at the total number of people who are conservative, and we say how many of those are male, 20 out of 29. Probability of being male, we say how many people total are there. There's 100, so we're going to do 46 out of 100. And we see that these two numbers are not equal. So this relationship does not hold true, and that means they are not independent. Question?
So an independent relationship, they would be equal to each other?
If they were independent, these two numbers would turn out to be equal. Okay? All right. Can I flip over to the next slide? Okay. If you see a question on the quiz asking if two things are independent, will you be able to test that out and answer yes or no? We'll feel okay? Okay, because you will probably see a quiz question on whether two things are independent. Okay? So you've been given fair warning about that. Okay. Okay. We have, sometimes we have or questions. Okay. So we could ask, what is the probability? So I'm going to say, I select a person at random. And I say, what is the probability this person is moderate or conservative? Okay? So we want to know, what's the probability that this person is moderate or conservative? Okay, so what is our answer here? Well, how many people are moderate and how many people are conservative? So our answer here is going to be, we're going to take the people who are moderate. Okay, so that there's 25 out of 100 who are moderate. How many people are conservative? 29, okay. So the probability of being conservative is going to be 29 out of 100. So our total probability here is going to be 54 out of 100, or 0.54. So when we are looking kind of at columns here, we just say the total number of people who are moderate, total number of people who are conservative, 25, 29, and we add those two together. Okay? Is that all right? Is everybody okay with this? Okay. What if I ask, what's the probability that someone is male or conservative? Male. Okay. So here we want to know, I'm going to select someone at random. Again, I select someone at random. What's the probability this person is male or that this person is conservative? Okay. And so this is an and/or. Okay, and it's what's the probability that this person is male and or this person is conservative? Okay, so in English, you know, we have two uses of the word or. We can say, do you like chocolate or vanilla ice cream? And then you would answer, I like chocolate, or I like vanilla, right? And then, but I could also ask the exact same question, right? So that question was, do you like chocolate or vanilla ice cream? Okay, but I could ask the exact same words, but if I change my intonation, it changes the meaning of the question. Okay, I could say, do you like chocolate or vanilla ice cream? And you would answer yes, right? Okay, so there's a difference here, and when we are in statistics, we take the second meaning of the word. Okay, so we're asking, what's the probability that this person is male or conservative? Okay, and you're essentially saying it's an and/or. Okay, do you like chocolate and/or vanilla ice cream? But we don't do that in our everyday speech because it would sound really pretentious. But what?
People start looking at it.
Right, but there is kind of a difference, and I guess I illustrated that just by emphasizing a little too much the pauses that we have. But yeah, so we're asking, is this person male or conservative? Where the answer is going to be yes or no, okay? Or what is the probability this person is male or conservative? So here it's essentially an and/or, okay? And so what is our answer here?
0.66.
Okay, I am getting 0.55. Okay. let's see how I'm getting this number, okay? So, or I don't know, am I adding up wrong? I think I'm adding up correctly in my head. Let's ask all the people who qualify as male or conservative. Do these 21 liberal males qualify for the question of male or conservative? Yes. Okay, what about these 5 moderate males? What about the 20 conservative males? Okay. The 25 liberal women?
No.
No. The 20 moderate women?
No.
No. What about these?
Yes.
Yes. Okay. So we would do 21 plus 5 plus 20 plus 9, and I think that gives me 55 out of 100. Is that right? Did I do my addition correctly? I'll just double check. Okay, yes. So that's how I get 0.55. Yes, question?
I'm sorry, can you clarify why moderate was chosen?
The moderate males?
Yes.
So what is the probability this person is male or conservative? So I've got someone here. This is a moderate, politically moderate man. Okay? Is this person male or conservative? And the answer is yes. Okay? So these groups qualify, and so we have a total of 55 out of 100 people that qualify in our answer here. Is that okay? All right. I could have gotten this another way, okay? I could have done probability of male plus probability of conservative, but I would have run into a problem here, and that is I would have double counted one of my groups. So I would need to subtract the overlap, which and we subtracted only once, so this would be the probability of male and conservative. So I would have 0.46 plus 0.29 minus the overlap, which would be 0.20. I went straight to the decimals, but I could do it in fractions. But is this okay? All right, and this would also give me 0.55. Yes?
On the quiz, are you going to ask us to do, find the
I will
answer?
ask you to find the answer, and you could do it either way you want. Okay? Now, if you didn't have the table, you might be forced to do it this way. Okay? We might have a situation where you don't have the table. So the general rule for OR questions is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which is what happened here. And it's technically also applies to the situation with the moderates and conservatives, except there's no overlap between the moderates and conservatives. When we surveyed the people and we said, please pick one of these political ideologies, liberal, moderate, or conservative, we did not give them the option of choosing more than one. So there's nobody who would qualify, who would have answered both moderate and conservative. So in that case, there's no overlap. Okay. In our simplified survey where we said you must be one of these three. All right. Questions? I've got reluctant smiles on people's faces here, so I'll take that as we'll keep going forward and hope for the best. I do have a practice quiz, and I think if you study that, it will help prepare for the quiz next week. And then I think the homework problems that have been assigned are also helpful. Are we okay? All right. Let's talk about then and probabilities, okay? And events. Or and situations. So we might talk about we might say you know, if it rains tomorrow, then the probability I go to the beach is 5%. Okay? But if it does not rain, then the probability I go to the beach is 40%. Okay? So symbolically, I can write this thing as the probability of beach given rain. Okay, the probability I go to the beach if it rains is only 5%. And 40% would then be what? Probability of beach. And what would I write next? Given not rain, right? Or no rain. Yeah. Okay. All right, so we check the weather, and the weatherman says the probability of rain tomorrow is ... 25%. Okay, this is not an actual forecast. All right, so we'll say the probability of rain itself is 25%. So then I ask this question. What is the probability I end up going to the beach? Okay, so this is interesting. Okay, so yeah, so let's answer this. Okay, so I could go to the beach if it's not raining tomorrow, right? That's one way we end up going to the beach, and then if it does rain, I still might end up going to the beach, right? It's just less likely that I'm going to go to the beach, okay? So we're going to map this out using a little tree diagram here, okay? We're going to say, what's the chance that it rains tomorrow? Okay, and what is, and then, or the other possibility is that it doesn't rain, right? So what's the chance that we end up going down the path where it rains tomorrow? 25%, right? I have that right here. Probability of rain, 0.25. So I'm going to say probability of rain. So the probability I go down this path is 0.25. That's right here. Okay? Which means what's the probability that it doesn't rain? What's that? 0.75. right? Because it's either going to rain or it's not going to rain. That's the only possibilities. So if it doesn't rain, I mean, if chance of rain is 25%, the chance it doesn't rain is 75%, 0.75. Everything so far so good? Okay, and if it does rain, might I go to the beach? Yeah, I might. Okay, and what's the chance I end up going to the beach? 0.05, right? So this is 0.05, and this is probability of beach
Can you explain that again?
given rain. Yes. So I've said right here, the first sentence here, if it rains tomorrow, the probability I go to the beach is 5%. So if I end up going down this path that says now it's raining, then I ask, what's the probability I'm going to go to the beach? That probability, according to this sentence, is 5%. Okay, so I write here. Okay, and then I might not go to the beach, so we'll say no beach. And what's the probability that I won't go to the beach if it's raining? 0.95, right? So once it's raining, I either go to the beach or I don't go to the beach. Okay, so once we've gone down this path that it says it's raining, I either go to the beach or I don't go to the beach. Probability I go to the beach is 5%. Probability I don't go to the beach is now 95%. Yes, question?
Can you write the equation similarly for no beach and not?
Yeah. So what would I write for no beach? This would be probability of, what would I write here? I would write no beach, and then I would write what? Vertical bar given rain. Okay. Okay, so then should I keep talking and walk you through this, or should I give you a chance to fill this bottom part out yourself? Huh? Okay. Well, you guys can do it yourself. Okay, so take a minute and see if you can put in the correct numbers and correct labels here. So I'll pause on YouTube also. And do it together. Okay. All right. Let's take a look. Okay. So if it doesn't rain tomorrow, then what could happen? I could go to the beach, or I might decide not to go to the beach, right? Okay, so if it doesn't rain, if it does not rain, then the probability I go to the beach is what? 40%, okay? So I'm going to put 0.40, and this would be probability of beach given no rain. And then down here, then if it doesn't rain, what's the probability I don't go to the beach? 0.60, right? And so that would be probability of no beach given no rain. Everything okay? Labeling this entire thing? Okay, so then what's the total probability I end up going to the beach? Okay, so to get that, we say, well, where do we end up at the beach? We end up at the beach right here, and we end up at the beach right here, right? So what's the chance that it rains and I still go to the beach? I would go 0.25 times 0.05. So I just go down the paths and I multiply. So I do 0.25 times 0.05, and I get what is that? 0.12? I don't know. What is that? 0.0125. So this is the probability that it rains and I go to the beach. So this is probability of beach and rain. So notice this is different because I used the word and not a vertical bar. Okay. All right, and then what's the probability I end up down this path? I would do 0.75 times 0.40. I just multiplied the numbers down those paths, and I get 0.3. And what is the label applied to this thing? This is probability of beach and what? No rain, right? So there's two ways for me to end up at the beach. It could rain and I still say, well, I really want to go to the beach today. And it could say, it could end up not raining and I say, I want to go to the beach, okay? So there's two ways I can end up at the beach. So the total probability of me ending up at the beach is going to be this plus this. I add these two together, and so the total probability I end up at the beach is equal to 0.0125 plus 0.3, and that gives me 0.3125, and that is my answer. What's the probability I go to the beach? This is the probability of beach is 0.3125. Yes, question?
Can you just add all those variables, like 40 and 5?
You cannot just add 0.4 and 0.05, okay? Because 0.4 happens only if it doesn't rain, okay? And so adding those two together kind of assumes that the rain and the not rain situation are equally likely, and that's not the case, okay? Yes?
You said earlier that the probability had to be somewhere between 0 and 1.
Yes.
What would happen if you had 2.6 for something?
It's not possible if you create this tree properly, okay? If you create this tree like this and you put in the numbers, it is not possible to end up with numbers that add up to more than 1, okay? Because when you create the tree properly with the numbers, the correct numbers, the truth is that all of these things added together will add up to 1. So it's not possible to go over 1. If you follow, I guess if you follow the paths and make sure your numbers are correct. Okay, does that make sense? The total probability I end up at the beach is I could end up at the beach with rain, I could end up at the beach without rain. The probabilities of those things are different, but I can combine them and get 0.3125. Okay, and so you know, what's the probability of beach and rain? You know, I had to multiply these things together. So notice when we started the problem, the only information that was given to you were these 3 statements up top. Okay? Everything else, this entire tree diagram or path diagram, we filled out ourselves using, you know, just some deduction from our heads here. Okay? All right. Is that okay? Let's talk about sequences of independent events. Okay. So in the previous thing, going to the beach and whether it rains or not, those were dependent events, right? Because the probability of going to the beach depended on whether it rained or not. Okay, when it rained, I was less likely to go to the beach. Well, if it doesn't rain, I'm more likely to go to the beach. So that means beach and rain are dependent. We have situations where we have sequences of independent events. So this could be something like, I decide to roll a die 4 times, okay? Okay, so you know, you got your little dice, 1, 2, and 3, and it's a and so you roll it, and you're going to do this 4 times, okay? And let's say we say, you know, what is the probability I get the number 6 all 4 times. Okay. So in order for this to happen, what has to happen on the first roll? First roll must be 6. Second roll must also be a 6. The third roll must be a 6. And the fourth roll must be a 6. Okay? Does this seem like it's going to happen very often? No. Is it possible though? It is. Okay. Let's figure out what the probability of this is going to happen. So what's the probability of the first roll ends up being a 6? 1 out of 6, okay? So I got a 1 out of 6 chance that I get a 6 on the first roll, okay? And then, let's say that does happen. What's the chance that I get a 6 on the second roll?
1 out of 12.
No, it's 1 out of 6 again, right?
Yeah.
So there's 1 out of 6 again, okay? So in order for this to happen, so far, I have to get a 6 the first time, so that only happens with 1/6 probability. I have to get a 6 the second time, and then it has to happen a third time, and then it has to happen a fourth time, okay? So it's not going to happen very often. What's the total probability that this is going to happen? It's going to be 1 out of 6, okay? And I have to raise that to the 4th power. So it happens with probability 0.00077. So this is 1 out of 6 raised to the 4th power, or 0.00772. Okay, so this happens less than 1 in 1,000. About 7 or 8 times out of 10,000 opportunities. So if you roll a die 4 times, 10,000 times, so that's 40,000 rolls, you might see, the number 6 4 times in a row, or all 4 times, about 7 or 8 times there, something around there. That's not even guaranteed. Okay, is that all right? Okay, so let's. I'm going to give you an opportunity to do something. Okay, so what is the probability I get a number bigger than 2 all 4 times? What's the probability I get a number bigger than 2 all 4 times? I'm rolling the die 4 times. So what's the probability I get a number bigger than 2 all 4 times? All right, do we have an answer? Okay, and then, so what do we do? So the first roll must be, what? Bigger than 2, right? So what's the probability that I get a number bigger than 2? 4 out of 6, right? Because the numbers 3, 4, 5, and 6 qualify as being bigger than 2. So the probability of that happening is 4 out of 6. And this has to happen what? All 4 times. So it's going to be 4 out of 6 times 4 out of 6 times 4 out of 6, or 4 raised to the 4th power. So what is that? 4 out of 6 raised to the 4th power. And I get 0.1975. Is that looking good? Okay. Hearing no response, I will continue. If anyone's confused, yes. Okay. Thank you for raising your hand. I'm happy to try to clarify. Do you have a question? You're just confused. Okay. So what we're doing is we're calculating the probability of this sequence of events, right? So what I'm saying is I'm going to roll the die 4 times, okay? And I want to make sure that I get a number bigger than 2 on all 4 of my rolls. Okay? So far so good? Right? So the very first roll, what has to happen? I have to get either a 3, a 4, a 5, or a 6, right? So what's the probability that I get a 3, 4, 5, or 6 on the very first roll? So there's 4 outcomes that are allowed, right? 3, 4, 5, and 6. Those are allowed. How many outcomes are there total on a die? 6, right? So a die is a cube. There's 6 sides. All are equally likely. So the probability that I get a 3, 4, 5, or 6 is 4 out of 6. Is that part okay? Okay, so that has to happen on my very first roll. Okay, but I want to make sure that it happens on all 4 rolls. So it also has to happen on my second roll, and it has to happen on the third roll, and it has to happen on the 4th roll. Okay, and so to calculate all of these things, essentially when they're independent, we just multiply these probabilities together. Is that okay? And so I've done 4 out of 6 times 4 out of 6 times 4 out of 6 times 4 out of 6, which is essentially 4 out of 6 raised to the 4th power, and I get 0.1975. Is that okay? Yes, question, Susan.
What about the roll that doesn't give you a 3, 4, 5, or 6?
So, what do you mean that?
You said
So,
we have to roll it. We have to roll the dice that get a 3, a 4, a 5, or a 6.
Yes. Yes. So when I write the number 4 out of 6 here, what I'm saying is that the other possibilities, getting a 1 or a 2,
Right.
don't happen. And that's why it only happens with the probability of 4/6.
I see.
Okay? And so that, I've got a 4/6 chance it happens on the first roll. But then even if I survive the first roll, then I've got a 4/6 chance that of making it through the second roll. And then if I survive that one, I get a 4/6 chance. So I'm asking, what's the chance that I get through all 4 rolls and I survive by getting, 4/6 every single time, right? It'd be, you can imagine some terrible game where you have to keep rolling the die. And, if you survive all these die rolls, maybe you win $100 or something. And so, the question is, maybe you keep winning more money as you keep rolling the die. How many rolls do you want to keep playing for? And you've got to balance, like, well, the next roll I might lose, but there's also more reward or something. So, is that all right? We'll try a few more examples that are even harder, and we'll see if we understand these. Because if you can understand the harder ones, then you can definitely get through the easy ones too. Okay, so let's try something out here. Let's say I have a big a bag here. I've got a bunch of little marbles. Or maybe these are M&Ms. Okay. So I got a bag of M&M candies here, okay? Huh?
Swedish fish.
Swedish fish, okay. But all the Swedish fish in America are red, right? They don't. And then I was told in Sweden they're different colors. Yeah, so that sounds like gummy worms to me, or gummy bears.
Swedish fish means Sweden is just fish.
Yeah, I know. It's just fish. Yeah. If you're a kid, do you say I want fish, and then they know you're talking about the candy or the no? Is that even a joke? Are puns funny in other countries, or is this just an American thing?
Only American.
Only America finds puns funny? Only I do? Well, that's unfortunate. Okay. All right, well, anyway, let's say we got a big bag of M&M candies, and let's say you had some crazy person who was like, I only like the red M&Ms and the green ones and the blue ones. Huh? They have black M&Ms? Yeah, but you've gone to some crazy person's house and they say, these are the only approved colors in my home. I'm gonna throw everything else away, okay? And I like the red ones more, so I'm gonna make sure that half of my candies are red. 30% are green and 20% are blue. So this is what makes up our bag here, okay? This is a contrived scenario here, but let's say in our bag, half of the candies are red, 30% are green, and 20% are blue. Okay? I'm just setting up some silly situation here. Right? All right, so now we will pick some candies out of the bag. Now what we do is we're going to pick the candy, we look at it, then we put it back in the bag and we mix it up, so therefore it always maintains these proportions of 50% red, 30% green, and 20% blue. Because technically, if we keep pulling candies out, it changes what's left in the bag, right? So we're going to look at the candy. We're not allowed to eat the candy. We got to put it back. We're going to shake up the bag. So every time we've got these proportions. Okay. So I'm going to here's a simple one, all right? If I pick two candies, what is the probability that both are red? So you think of the sequence that has to happen. Yeah, so the first candy has to be what? Red. And that happens with probability 0.5. And then the second has to be also red. And that happens with probability 0.5. So our total probability is going to be 0.5 times 0.5, which is 0.25. Is this sequence okay? I want to make sure that the ones who were confused earlier are okay with this one. Good? You're good. Okay. And, okay, so let's try another one. Okay, I will pick two candies again. Okay, and I'm going to ask, what is the probability the first is blue and the second is green? How often does that happen? Okay, so the first candy has to be blue. What is the probability that the first one's blue? 0.2. What's the probability that the second one is green? 0.3, right? And so I do 0.2 times 0.3, and what do I get? 0.06, right? It's very important that when you do 0.2 times 0.3, you get 0.06, because 60% is way bigger than 6%. Okay? Is this okay? So far, so good. Okay. What about this one? All right. So I will pick two candies again. Okay. What is the probability that I end up with one blue and one green. Okay. Can we see the difference between this question and this question?
Yes.
Yes, right? Okay, so in this one, the order doesn't matter, right? So there's two ways I could end up with one blue and one green, okay? One way one is the first one is blue, so I'm just gonna write one is blue, and the second one I draw is green. And what's the other way? The first one is green, and the second one is blue. Is that okay? So this one happens, we calculated earlier, is going to be 0.2 times 0.3, so that gives me 0.06. And what's the probability that this order happens? Well, probability that the first one is green is 0.3, and the probability that the second one ends up being blue is 0.2, so I also get 0.06.
So they're independent.
So, yeah, the sequences are independent, but what's the total probability that I end up with one blue and one green? I add these two together and I get 0.12, okay? I want to make sure we're okay there. That's also okay? All right, so I got smiles and a head nod. You don't understand? Okay, so the question is, what's the probability that I end up with one blue and one green, right? We're looking at candies, and so I'm going to take two of them, okay? So there's two ways I could end up observing one blue and one green. One way is I get blue on the first, and then I get green on the second. And what's the probability that that's going to happen? It's going to be 0.2 for blue on the first times 0.3 for green on the second. That's okay, right?
Yeah.
Okay. That one's okay, right? But I could also end up getting blue and green by seeing green on the first and blue on the second. And that's a distinct event from blue on the first and green on the second.
Say that part again.
So getting blue on the first and green on the second is different from getting green on the first and blue on the second. Right? It's different if your first child is a boy and your second child is a girl. That's a different situation than if your first child's a girl and your second child's a boy, right? Those are different situations. And the end result is you end up with one boy and one girl, okay? So I don't know, if you had the Hunger Games, then both of your children might be at risk at some point. But, you know, and the end result is you have one boy and one girl, but you have different, I don't know, different family dynamic, I guess, or whatever, if the older child is a boy and the older child is a girl. Those are different situations, so we have to treat them as different situations. But it turns out the probability of boy or blue-green is 0.06, and the probability of getting green then blue is also 0.06, okay? But they're different things, so we get 0.06 and 0.06, and the total probability of getting either this scenario or this scenario, we add those two together and we get 0.12. Is that okay? Somewhat.
What's the difference between those situations being completely random versus the situation that we see values given to us and the order given to us?
Yeah, so this one, essentially, you know, maybe, well, it's convenient that I've got B and G for boy and girl, but, you know, so the second question that I have here is, you know, what's the probability, this is like, what's the probability that your first child is a boy and your second child's a girl, okay? And that's going to be a different answer from what's the probability that you end up with a boy and a girl after having 2 kids, because the first one only allows for the oldest being boy and the second being a girl, whereas what's the probability you end up with a boy and a girl after 2 kids allows for either possibility that the older one's a boy or the older one's a girl. So, yes.
So what if it asks if you end up with 1 blue, 1 green, and 1 red? Then you
Yeah, then it gets even more complicated, because then you have to list out all the possible sequences that would be allowed, calculate the probabilities of each of those sequences, and then add all of those together. Okay, so I kept it simple here, but you're right. If we had a more complicated thing, we're gonna pick 7 candies. What's the probability that 2 are blue, 1 is green, and 4 are red? You have to calculate every single possible sequence, the probabilities of every single one of those sequences, and then add them all together. Okay. There's a formula for doing that. It's called the multinomial probability, but I don't think you guys really are worried too much about that, okay? You have to know this if you're going to teach statistics, but yes. So, for simple situations like 1 blue and 1 green, we can think of all possibilities. Yes? Yeah, I don't want to give you a formula per se, because I think the formula is going to look more complicated than you want it to be. And I think it's easier to think about what the problem is asking and do the math that way.
Can you give us a formula, because my brain thinks the other way?
I don't think you'll like the formula.
I literally have an easier time looking at formulas.
Okay, I will show you what the multinomial formula is, which is what you are asking for.
Oh, you don't? Oh, it's not from the book?
We'll put this in
Yeah, it's not in the book, but okay. So this is the multinomial formula right here. Okay, so yeah, so
Of course. I knew the variance.
yeah. So yeah, if you want
No, I meant the formula for 2 variables. The one, the
yeah, so that's going to be binomial, and I think
binomial.
that will show up next week. But again, we're going to just learn a simplified, abridged version of the binomial, okay? Yeah, and I don't, yeah, this stuff, I don't have this memorized, but if you ask me to calculate something, I know how to input it onto the computer to get the answer for you. But yeah, okay, so don't worry about it, okay? Let's, let me,
Take up your entire front page of your midterm note card.
yeah. Okay, let's continue on with our silly situation. Okay, so here's one that we can deal with. Okay, so I will pick 3 candies. Okay, what is the probability that none of them are blue? So I'm going to get 3 candies, and I want to know what's the probability that none of them are blue. What's that? Yeah, so, okay. So think about the sequence that has to happen, right? So I'm going to how many candies I'm going to pick total? So I'm going to have a first piece, the second piece, and the third piece, right? Okay, the first piece has to be what? Red or green, okay? So it has to be not blue, okay? So it has to be not blue, which means red or green. Okay, so what's the probability that I get a red or green piece of candy? 0.8, right? Okay, what has to happen on the second candy? Same thing, right? So I'm going to also have 0.8. Okay, and the third candy also has to be same thing, so I'm going to have probability of 0.8. Is that okay? So I have to get not blue, and not blue. So it's going to be 0.8 times 0.8 times 0.8. So that will give me 0.8 times 0.8, 0.8, 0.512. Good? Okay, so I got people bobbing their heads like
Getting my money's worth.
that's good. Okay? Yeah. Okay. Here's a question. Okay, I will pick 3 candies. Okay, what is the probability that I get at least 1 blue candy? No. Okay, so this one's a little you got to think, okay? So the probability of getting at least 1 blue candy means I get what? I can get the options are I can end up with 1 blue candy. I'm also allowed to get 2 blue candies, or I could end up with getting the magical 3 blue candy unicorn, right? It doesn't happen often, but I could end up getting all 3 pieces are blue, right? So these are the situations that qualify as at least 1 blue candy. Is that okay with everybody? Okay. What is the only situation that does not qualify as at least 1 blue candy? No blue candies. This is where we go home sad, right? So this one is the only one that is not allowed. Okay. So I haven't done the math, but if I did the math and if I add them all up, these would all add up to what? No, they would add up to 1, right? Because these are probabilities, right? So if I do the probabilities of each of these outcomes, one of these things must happen, right? There's no other possibility. If I take 3 candies, I'm either going to end up with 0 candies that are blue, 1 candy that's blue, 2 candies that's blue, or 3 candies that are blue, right? Is there any other possibility that could happen? That's it, right? So one of those must happen. So that means if I add all of these up, the probabilities of all of these combined must be 1. Okay, does that make sense? No? No? Okay, so right, if we say something must happen, the probability of that something is 1. Okay, and we can break that apart into different percentages, right? So we could say, I could say, I'm going to flip a coin, and it could land on heads or it could land on tails, right? I could say the probability it lands on heads is 0.5. The probability it lands on tails is also 0.5. And if I say, what's the probability that I end up getting heads or tails? And you would say 100%, right? That's it, right? You can't get anything else. What's the probability that you end up with heads or tails? 100%, okay? So I'm asking, what's the probability I end up with 0, 1, 2, or 3 blue candies? And you would say 1, right? Okay, so when I say at least 1 blue candy, I know that everything over here has to add up to 1, which means if I can figure out the probability of no blue candies, then this plus this has to add up to 1. If I figure out this piece, then I have this thing. Do I know the probability of getting no blue candies? Yes. And what's that answer?
1 out of 3.
0.512, right? I will pick 3 candies. What's the probability that I get none that are blue? That's no blue candies after 3. I know this thing is 0.512. Okay? Which means this part over here has to be,
512 minus 1.
yeah, 1 minus 0.512. And I get 0.488. So what is the probability I get at least 1 blue candy? The answer there,
Wait, how'd you get
0.488. Because I said this plus this have to add up to 1. So this thing is equal to 1 minus 0.512. Because I know this thing plus this thing must add up to 1. Yes? Yes. Are we okay getting 0.488 here? Yes.
For stats, is it always the final answer like that, or are you supposed to change to a percentage, like say 48.8%?
Okay, so if we want to be pedantic about this, when it says the probability, you should answer with a decimal between 0 and 1. If it asks for a percentage, then you convert it to a percentage. You know, when I have answer choices, just pick the one that's correct. I'm not going to have both 48.8% and 0.488 as an option. Just pick the one that's correct here. Okay, well, study these examples. I think they're good. Look at the practice quiz that's posted online, and we'll see you guys next week for your quiz on probability.